Okay, so welcome everyone. I wanted to first thank Father Bardis and all the organizers of this event for having me here, for inviting me to come talk to you about the topic of tonight, God and the quantum. So a little bit about me. I was born in Texas. I went to Texas A&M University for my undergraduate degree. My PhD is just up the coast from here, UC Santa Barbara. Is my PhD in physics. At that point, I married my lovely wife, Marion, who's right there, and we moved to Geneva, Switzerland for 3 years for a postdoc. And so then after that, we moved back to the United States, and I've been at the University of Rochester since 2006. Okay. So my specialty is quantum physics. I read a lot of papers about that. I have a lot of students. One of my students, former students, is right next to Marion. It's Justin. He was one of my students. He's here actually on the faculty at Chapman. So I'm here because I'm working with Chapman people, Justin among them, Drew, and a bunch of other people that are just next door. I'm also a Christian. So I was raised in the Episcopal Church. I became a member of the Catholic Church a few years ago. I'll tell you a little bit more about that. And so the topic I have for tonight is a challenging one because there's just so much to talk about, right? So we're going to be talking to you about God, but also the quantum. And each one of these things we could have a whole course about. So I want to begin with a sort of some common attitudes often people talk about when it comes to science and religion, because everyone has an opinion about that. And I want to just sort of highlight a couple of common ones. So here's a common one. So you often hear this in places like the New York Times or something like that. Science is some objective, logic, fact-based stuff. There is some conclusions arrived at based on evidence, and this points to a materialistic, atheistic account of the world. This is something you hear quite often. What is religion? Religion is sort of the opposite of that. It's some irrational, emotion-driven thing. It's some private thing you would do in your house in the privacy of your own home. You don't talk about it in public very much because it's embarrassing. It's sort of glorified superstition and ignorance. And it's just really basically a pre-modern way of trying to explain the scary world that we live in. All right, so you hear this sort of thing a lot. And I just want to begin by pointing out sort of what's wrong with this common attitude. Because there's a lot wrong with it, and I can't unpack all what's wrong with it here, but I want to give a couple of points. And the first point is that this picture of science is sort of the glossy magazine picture of science. As someone that does science for a living, science is a messy business. I fight with people all the time about scientific things. People fighting with each other all the time about scientific things. We don't agree on many things, but we fight things about many things. So this idea that you sort of read about in textbooks, say you sort of follow the scientific method, you have a hypothesis, you make some experiments, you draw some conclusions, and that's the way science advances. Most of us that actually do science realize the process is very different from that sort of textbook view of how things are going on. And the other thing that we want to stress is that, so I love science. I do science for a living. That's how I make my bread and butter. But it's a limited thing. And I'll talk more about my view of science later, but I want to stress in the beginning, it's very limited. What it can say things like? It can say things about patterns in nature. And that's really all science can talk about. And so in that sense, if you want to ask about, for example, what's the meaning of your life? Or do I love this person? Or, what should I do next Tuesday? Science can't tell you about any of those things. So it's really an extremely limited point of view. But it's very powerful in its domain of validity, but people try to push that domain of validity much more broadly than it's really meant to be. So the second point I'm going to make is about religious thought, and there's this sort of common idea that religious is an irrational thing. And I think certainly there are some religions I could point to that kind of help reinforce that point of view. But most religious thought, that I've been raised in and I'm accompanied, that I've been have an experience with, is actually a very rational view. So we'll talk a little bit about that. But this idea, even the idea of theology, this idea of the study of God, is based upon trying to have a systematic approach to our encounter to answer the questions: why are we here? What is God? Who are we? What's our place in this world? And so, in my experience anyway, and I'll talk about this later, religious thought can also be irrational and not irrational, a rational and evidence-based thing. And furthermore, it's not bound by the same kind of bounds that science is bound. It can consider questions that's forever close to scientific community, like those things I was talking about just a moment ago. Why am I here? Who is God? What should I do next Tuesday? Those kind of questions, they can help you kind of answer those kind of questions. Okay. All right. So I want to give you now sort of another very common point of view, which is that science and religion are both fine and valid things, but they simply have nothing to do with one another. They're just completely separate domains. And this is another very common attitude. Somehow the cartoon version of this is that science explains the how of the world. So it gives you some phenomenon's objective explanation, and it's complete in its domain. Whereas religion kind of tells you, it can give you sort of a gloss on that. It can tell you why, in some sense. It's sort of subjective. It exists really only as a philosophy. It can inform things like morality, and perhaps tell you about some motivations, but really it's a bound thing. And so one sort of nice summary of this point of view is by Stephen Jay Gould, and he has this concept of non-overlapping magisteria. And the idea is that you have this magisteria of religious thought, and people sort of decide what are the correct ways of living your life, and what are the right ways of morality and points of view. And then there's the scientific magisteria. That's people like me, the scientific experts that get to decide what science teaches. And those two just don't have anything to do with each other. And so you don't ever talk about what happens when you bring them together. But in my experience, this is also not a satisfactory view because often these questions that science is asking, religion is also asking, can also come crashing together in ways that generate a lot of heat and light. And so a couple of examples you probably know about, sort of the origin stories, the origin of the universe, the origin of man is a hot topic. Can miracles happen? What is man? What is consciousness? These are things that, in some sense, both science and religion have a legitimate right to talk about, and yet, so I think those are clear points of tension that go beyond this idea of just having nothing to do with each other. Okay. And I guess the other point I wanted to make here is that if we adopt this point of view that science basically controls all observable phenomena, and faith has to sort of retreat into some kind of meta-narrative, I think it becomes essentially disconnected from life. It becomes really an irrelevant and pointless exercise. Okay, good. All right, so I want to talk now about the two intellectual approaches between science and religion, in my view. So the first thing that I want to say is that both religious thought and science, I think of as kind of cousins. And they're cousins because they're committed, first of all, to the truth. After all, that's what we're interested in. We're interested in finding out truths, and not everyone is interested in that. For example, there are some social scientists that don't believe in truth. Truth is some consensus-constructed idea, but at least traditionally, science and also religious thought is committed to try to understand what the truth is and then conform our lives in light of that. So we don't go along to get along, so to speak. We fight a lot, right? And because we use the rational approaches, we use rational approaches to arguing about the correctness of science and also religion. There's a lot of arguing going on. So people fight a lot in both of these disciplines, which is why they're somehow cousins to one another. All right, so I want to talk about this. So these are the common things. But there are also some divergences or tensions. They're not the same thing. They're sort of very different things. And so one of the differences is that science is never finished. It's always open to revision because in principle we can always discover something new that contradicts or at least extends our previous view of the world, whereas religion has an element that science doesn't have. So religion has this element of revelation, the idea that something external to us can come in and tell us something as a primary source of belief, okay? And so each of these has its own, what I call, oh, that's exciting. Okay. Each of these has its own sort of pros and cons. So the con is that science can be, in principle, be falsified, but it's also, again, limited to the controllable and the repeatable. Okay. All right, so now that sort of ends my initial blurb about science and religion, and now I'm going to tell you about quantum mechanics. So quantum mechanics is a really cool area of science. I like it a lot. And so here are some of the strange phenomena in quantum mechanics that extend our view of the classical world. So some of them one of those is that energy now becomes a discrete variable. So in classical physics, energy is always continuous. I can roll a ball with such and such a speed, or if I have if I compute the energy of say a planet around the sun, it has a certain energy, and that energy can be anything you want. In quantum mechanics, that's no longer true. Energy becomes discrete or quantized. That's where the name quantum mechanics comes on. It only takes certain discrete values. There is some weird stuff going on about particles and waves I'll be talking about in a minute, but this introduces some new ideas, something called complementarity. There are some famous thought experiments that have emerged from deep in the early days of quantum mechanics. One of them is Schrödinger's cat, you probably heard of, about trying to exist in disjoint states of reality at the same time. A cat is both alive and dead at the same time in some sense. There is weird stuff about non-locality we'll talk a little bit about. EPR stands for Einstein, Podolsky, Rosen, as one of the inventors of a great thought experiment that have been inspiring physicists for a long time. This goes with a concept called entanglement, where I have to have a global joint description of, say, two or more parties at the same time. I can't really describe them completely in isolation. And then really interesting stuff that I work on a lot about quantum measurement and how measurement, the act of making a measurement, changes the quantum reality. That I can't have an isolated system, but if I want to learn something about an isolated system, I must fundamentally change it. That's something, a new feature that emerges. And then also this leads to this idea of the observer versus the participant. I can't just passively observe, I have to somehow become a participant in my own experiments. All right, so we'll try to unpack some of these ideas. So first of all, the physics, what is quantum mechanics? It's the physics basically of small things. There's a characteristic scale associated with it. We write it as h with a slash through it called h bar, and it's called Planck's constant. So that gives you a characteristic energy scale. So it's something like 10 to the minus 34. It has units of J, which is a joule, which is a unit of energy, and S, which is a unit of seconds. And so it's a really small thing. If you're familiar with scientific notation, it's really, really tiny. And so that's why it's sort of important, most important for small things. And then things like particle properties, like the particle's position or its velocity, no longer take on definite values. They become indeterminate. And in fact, if I try to measure them, and I measure where the particle is versus what its velocity or its momentum are, the momentum is just the velocity times the mass, there's an important uncertainty relation derived by Heisenberg that says the product of the uncertainty of these two things is bounded by this new constant I was just talking about. Okay, and this new constant is really powerful. It leads to things like the atoms have a finite size. The atom is about 10 to the minus 10 meters. Again, something really tiny, but I can derive that just by knowing a little bit about energy and applying this Heisenberg uncertainty relation. Okay, so that's a quick introduction to quantum, the basic idea. The next point I want to make about quantum mechanics is not just some one-off theory that we can brush aside. Quantum mechanics is our best theory of nature. Okay, it is our most precise, most quantitatively exact predictions about nature, and it's in best agreement with what we see around us. So one example is if I calculate a single electron, I see it acts like a little bit like a bar magnet. It has a what we call a magnetic moment, and that magnetic moment is proportional to something called spin, which is an intrinsic quantity of the atom. There are some fundamental constants here: the electron charge, Planck's constant, the mass of electron, the speed of light. But then there's also this funny number out in front, G, which we call the anomalous magnetic dipole moment of the electron. Okay, so if you calculate, if you use one of the equations of quantum mechanics called the Dirac equation, naively you think that's going to be 2. Okay, but it turns out it's not 2. When you measure it, it's actually, if I take it and I subtract 2, divide by 2, I get this number from experiments. So this is some experiments that were done over many years. This is probably the most precise one. And if we take our best theory of nature, quantum electrodynamics, augmented with quantum chromodynamics, I compute this perturbatively. It turns out you can't compute this exactly. You have to do some perturbative calculation. They've done this up to 5th order in some small number called the fine structure constant. This is the result of that calculation. Okay? So what you find is you find agreement to more than 10 significant figures. So it shows that this is an extremely precise, extremely accurate theory of nature. Okay, so it's a big deal. So we need to, but here's the amazing thing about quantum mechanics is that we have all the rules for calculating things. We know how to calculate this. This is a well-defined procedure. But people don't agree on the reasons behind the theory. People's interpretations of quantum mechanics is very different, and I'm going to get into that in a little bit. So here's a little cartoon. So one of the first things is that you have many strange physics. So this precise theory has many strange features. One are these what we call the quantum paths. You can't quite see them, but this is quantum paths. And what do I mean by that? And I can illustrate that with a little simple thought experiment. And the thought experiment is, I imagine I have a little gun here that's shooting out bullets or BBs or marbles or what have you. And I have a wall here, and in the wall there are 2 holes. And so the little bullets can get through either hole 1 or hole 2, and eventually they come and they hit in this backstop. And I ask, where do they land? Okay? And what you find is that in that experiment, I get some distribution, a scatter of where these guys land. And if I have it go through slit 1, I have this distribution of particles. If I have it go through slit 2, it's this distribution of particles. And when I have them both open together, what you find is the distribution of particles, no surprise, is just the sum of these two. Essentially, it's like either I go through hole 1 or I go through hole 2, and I build up this distribution of particles on the back of this detector. Now, if I do the same experiment now, where I keep everything the same, but I put some waves in there. Suppose I go on a lake, for example, and on the lake I have a wall, say a dock, and there's a dock with a hole in the dock, and I start splashing here, your little child starts splashing here. I track the wave trains. Well, the waves spread out in a circular ring. You've all seen this on the pond. And what happens is that those rings start going again through these 2 holes. And what's interesting now is that these 2 rings can start combining with each other, and you get what they call interference. So, who have not heard of interference? Just as a a few of you, but most of you have. All interference is when the peak of one wave combines with the peak of the other to make a peak twice as high, or the peak combines with the trough to give no peak at all. So you can do this in your own bathtub. You can splash together and see how the waves combine, and that's all that is. That's interference. But so if you look at the heights of these waves in the back of this detector, what you see is that you get, instead of this double pattern, you get this sort of wiggly pattern, and that's this interference phenomenon. Okay. So all that is just the big peak is simply where the crests combine or the troughs combine. Where there's no intensity at all, that's just basically where the peak combines with the trough, and so it's quite easy to understand. So now I introduce these 2 things to now tell you about another experiment. Suppose I have an experiment now with light, where I have a light, say a laser, going through a single slit and then double slits, and then I look over here to see what the relative brightness of the light on the screen is. And what you find is when you do this experiment is that you'll find this kind of alternatively light, dark patterns over there. And so the conclusion you might draw then naturally, well, we know clearly now light must be a wave, right? Because I just showed you how the water waves do the same thing. But the weird thing is that further experiments showed light doesn't just behave like a wave. Light also behaves like a particle. So it turns out that if I have a very sensitive detector there, and I turn the light intensity real down, real low, what I find at this detector, for example, back here, is not just a continuous stream of light, but I start getting discrete bundles of energy coming to me. So if I have a detector, the detector would sit there for a while quietly, then it would go click, and then it would sit there quietly for a while, and it would go click, and so on and so forth. And those little bundles of clicks, we call those photons. So these are the particles of the light field. Okay, and there are lots of other ways we can detect photons too. But now something is puzzling. If indeed there's something that these are actually particles, we can think about this experiment, for example, not just with light, we might think about them with something more particly like electrons. Suppose I spin out electrons, they go through these 2 slits, they arrive here on the screen. What I find is that on a single electron by single electron basis, is that these guys have to form this interference pattern over here. And so there's something puzzling about that, because for the interference pattern to emerge, every electron only goes through one slit, but for the interference to happen, it somehow has to know about both slits. So in some sense, a single electron has to go through both slits at the same time. And that's the first weird thing about quantum mechanics. And this idea of going at the same time is called superposition. The electron exists simultaneously going through the upper path and going through the lower path at the same time. Okay, so we have to revise our view of what these things are. We might call them particly electrons or wavy particles, or really neither. Okay, so this is a picture of an experiment where I have these single electrons going through. So at the beginning of the experiment here in this panel, there are only a few dots that are seemingly random. But as we do this for a longer time, we build up more and more events, and eventually you get these bright and dark spots showing the sign of this electron interference. Okay, so this is our first weird thing about quantum mechanics. All right, so let's go on. Let me tell you a little bit about the formalism, how we describe quantum mechanics. So in classical physics, it's fairly simple. The way you describe a single particle is just with some coordinates. We might describe it with a particle, so we're going to have a pendulum, and describe it with its position and its velocity or its momentum. And so as the pendulum swings back and forth, I can plot essentially either the position or the velocity as a trajectory in time, and that's the way we describe particles in classical physics. Okay, we can have more complicated kinds of dynamics, but the basic principle applies. There are just these two coordinates, position, momentum, and then I can then describe the physics of that particle with just those two coordinates. In quantum mechanics, it turns out we have to do something else. We have to introduce a new kind of coordinate. Sometimes we call it the wave function or the quantum state. And this wave function is a weird thing. It's an extended object. So here are some pictures of them. This is relevant, it turns out, for hydrogen, that first element of the periodic table you may remember from your chemistry class. So these are some ways in which the electron can exist in a hydrogen atom. And this is our new kind of quantum coordinate. So this object is a mathematical thing, and operationally what it does for us is it encodes statistical predictions about future measurements on the system. Okay? And so this is one of the new ingredients quantum mechanics adds, and this was discovered by the Austrian physicist Erwin Schrödinger. So this is our new quantum coordinates. And when we start talking about that, I'm going to make it a little simpler here. I'll talk about not just a particle, but just something with two possible values. So in computer science, we might call this a bit. It's either a 0 or a 1. So in quantum mechanics, we don't just say it's either a 0 or 1, we say it can exist in a superposition of 0 and 1 at the same time. So we would write some little formula here that tells you what the so-called probability amplitude of being in state 0 or state 1 is all at once. Okay? And so the interesting thing about quantum mechanics is that it's not a deterministic theory like classical mechanics is. If I prepare a quantum system in exactly the same way and I do multiple measurements on it, I find different results from the same initial conditions. So this is one of the other weird things about quantum mechanics. It's not a deterministic theory. Now you might say right then and there, wait, stop. If it's not deterministic, how can we have any science at all? It's like trying to predict, what your teenage daughter is going to do in 3 nights, right? You lose all predictability, everything just becomes chaos. And so what quantum mechanics does is it backs up a level. It says, I'm not going to predict every event. I'm just going to tell you what the odds are of the event. I'm going to give it a statistical theory. I'm going to tell you what the distribution of these results are. And that's what this wave function thing is doing. It's telling you what the distribution of these possible results are in a probabilistic sense. Okay? And so that's what this wave function does, is it tells you the odds. And so I can measure this, and for example, if it's 0 or 1, and this wave function tells me the odds, I'm going to find one or the other. Or I can measure it some different way. It turns out that I can measure it looking along in some different way. Like, for example, if you know about polarization of your sunglasses, polarization works a similar way. I can turn my polarizer the other way and measure it some different way, and then quantum mechanics tells me about that. Okay, so the funny thing about quantum wave functions is that they collapse. And so this is one of the other interesting features about quantum mechanics, is that the way you describe it is that the wave function is this in isolation, but as soon as I come along and I measure it, I only find one or the other. I found either result 0 or 1, and so then I have to change the wave function. So the wave function is no longer in that original state, it's been changed by the act of me measuring in that, and we call that wave function collapse. Okay, so I don't ever see these superpositions between 0 and 1, I only see one or the other. Okay, so this is one of the other funny things. All right. Okay, so let's explore that a little bit more. So here's another weird feature about quantum mechanics. This was a thought experiment introduced by these gentlemen. And I love this. This is from the New York Times, 1935. Einstein attacks quantum theory. Scientists and 2 colleagues find that it's not complete, even though correct. Okay. So this was Einstein, Podolsky-Rosen's thought experiment. And the idea that they had is, I'm going to prepare, this is sort of a modified version of their argument. I'm going to prepare not one object, but 2 objects in some one of these entangled, so-called entangled states. All this is a sort of a superposition of being one of 2 things together. So that particle 1 has a property that's perfectly correlated with particle 2, represented in terms of some wave functions. Then I send them far away from each other so they can't communicate with any kind of light signal back and forth between the 2 of the other. And then I'm going to measure that property on one party. I'm going to measure the party on the other property. And then EPR, Einstein, Podolsky, Rosen, argued that because you have to have these correlations preserved across space and time, that showed the theory that couldn't be. So the theory must therefore be incomplete. And so the interesting thing is that when you do the experiment, if I measure one property here, I find an answer, and I can tell immediately what the property is over there. But if I so suppose I had 2 properties like color and shape. Okay, if I measured, for example, blue here, I knew immediately this guy had to have the other color red. But if I had some other property, shape is not quite the right thing. But if I measured also shape here of square, for example, then I know this one was a square circle. So Einstein argued that this couldn't be true, and so that suggested there was something beyond quantum mechanics. Maybe quantum mechanics was just a statistical theory, but there was a deeper underlying reality that I could ascribe perfectly well-defined properties to. So there are well-defined properties. You know, this nonsense about the particle going through the left slit or the right slit at the same time. No, it only went through one, but we just didn't know it in some way. So maybe there's some theory like that, and we just have to average over some kind of fluctuations. So that idea all changed in a very dramatic way in 1964, where a man named John Bell derived a certain kind of inequality. And the claim is that you made very general assumptions about the nature of reality, about how these so-called hidden variables that Einstein talked about would work. They had certain definite properties. They behaved in the way that our ordinary classical intuition told us to do. And they were local. In other words, they can't change things across the universe instantaneously. What Bell did is he derived an inequality that all such theories had to obey. Okay? Whereas so the equality had to be less than, some mathematical combination had to be less than 2. This was Einstein's thing. But quantum mechanics predicted it can be bigger than that. It can have stronger correlations. So root 2 is the quantum mechanical prediction. And so this became a big debate. Which is right, Einstein or quantum mechanics? And so the claim is that if you violate this inequality, then you've ruled out this so-called local hidden variable. So what happened then is experiments were done, and they found that this inequality was in fact violated by nature. So every theory that you like, the kinds that we sort of intuitively like, the local theories, the ones that only affect things within the speed of light, and the ones that have definite properties that we like to think about, I'm definitely here or there, I'm not in the book at the same time, all those theories are ruled out by this experiment. So our classical view of reality has to be fundamentally altered in order to take into account. So this was really a revolution in quantum mechanics. Okay, so that's quantum non-locality. So let me go on. And so the next thing I tell you about is one of the neat things that I think about is what we call one of the great physicists is named John Wheeler, And he had this sort of weird view of the world that I wanted to share with you, because I kind of like it. And the idea is that this is sort of illustrating the classical view of the world and the quantum view of the world. And the classical view of the world is that we're sitting back, observing the world through like a pane of glass. There's the universe out there, we're sitting there, we're the observer, we're passive, we're detached from that reality. Whereas in the quantum world, that view has to completely change. And the quantum view is that it's just so weird, I love this. He has to smash through the glass with his hand, and his hands no longer are hands, they become like little meters looking around at things, and his eyes, it's just so weird. And so what that is showing you is, in his view, that we can't remain passive participants in the quantum world. We're fundamentally part of the experiment in some sense. And so this is just reflecting this new understanding about how measurements change the reality and so on and so forth. Okay. All right, so let's talk a little bit. So what is the wave function? Lots of people have different opinions about this. Is it objective? Is it subjective? Does it really exist before I measure it? Does quantum change the reality or merely reveal it when I do this measurement? Lots of interesting questions we can ask about this. So there are lots of people have lots of opinions about this. I made the mistake. So I gave this talk, or actually not this talk, but a sort of a version of this talk a couple weeks ago. I was at a conference in Pittsburgh on Christianity and quantum mechanics. They invited me to come speak about this. And I made the mistake of giving them, at this point, my view of the quantum interpretations. And that was a mistake, because then everybody wanted to poke holes and ask about what I really thought about my interpretation. I'm not going to do that. I learned from my mistake. But I want to go to the next thing and tell you that we know a lot of things objectively about the wave function based on experiments. That's the great thing about doing science, is that we do experiments and then begin to refine our views. So with some of the work that I've been involved with in the past, say 10 years ago, is we know a lot more about what this wave function is and what wave function collapse is, and I've been involved with some experiments to show this. That isn't that sometimes people try to describe it has something to do with something called decoherence. It doesn't. If you don't know what that is, don't worry about it. It turns out it doesn't have to happen instantaneously or abruptly. It can happen continuously in time. It can be gradual. It can be abrupt. It can happen near or far. It's sort of like a Dr. Seuss cartoon, right? It can happen near, it can happen far, it can happen slow, it can happen fast. And we have a very precise theory about the state disturbance, how the wave function gets partially collapsed, and we can calculate that, and experiments can test that and verify that that's the case. And the thing that I will say that's a little bit of a clue is that it all coincides with our information gain about the quantum system. That if we think about the wave function as a kind of proxy for information about the quantum system, then that's consistent, at least, with this point. Anyway, but this is some of the new stuff we've been learning about in the past 10 years or so. Okay, good. All right, and so one analogy I think of, so this is this little cartoon I published in Nature a few years ago, is we can think about this wave function collapse as sort of like a collection of butterflies, all prepared in some initial cage. And rather than just collapsing to one of two options, say the left tree or the right tree, as our two quantum options, we can actually track what's going on and actually sort of follow the path of the butterfly as it goes from point A to point B. So that's some of the new knowledge truth gain. Okay. All right, so I want to sort of wind down the quantum part. I'm going to segue. We're going to have like a little sorbet course about metaphysics before we move into the religion. So the metaphysics is that there's a whole field of quantum stuff called quantum interpretations. And so I've been involved with this, Justin's been involved with this, many of us play with this. But I want to stress to you, this is not science. If anyone tells you quantum interpretations is science, they're lying to you. This is metaphysics in disguise, right? And so the idea is that we have some experiments that we do, and we get results. And that's all, again, that's all science tells you what we can expect from science, is what the results are and what the, what the predictions of the theory are. But many people are not satisfied with that. Again, so this gets back to, again, religion and our sort of our role as human beings in this process. We want to know more. We want to know why. And so quantum interpretations is sort of the storyline that's going through your head as you're looking at the results of all these measurements. And there are lots of storylines. So the original one is the so-called Copenhagen interpretation. This was worked out by the founders of the theory. that these properties of the particles don't exist until they're measured, after which they're real. And there's sort of a modern version of that called the Bayesian interpretation. Only my information about the quantum world is real. There's one that goes back way, actually quite early to Louis de Broglie, who's also one of the founders of quantum theory, but was taken up again by David Bohm in the 1950s, called the Bohmian interpretation, or the pilot wave. So the process, there's a hidden reality called the pilot wave that you can't see, and it guides the seen particles, which are the real things. But the only problem with this theory is that these pilot waves, or the quantum potentials, have to change instantaneously across the universe to account for the fact. So this is an example of what's called a non-local hidden variable theory, not the local hidden variable theories that were ruled out by Bell's inequality. There's also the Everettian interpretation, the one I love to hate, so-called the many worlds interpretation. So this is the idea here: is that every time a measurement happens, the universe literally splits in two. So for every possible option, we have many universes that split from one another. So there are infinitely many parallel worlds being created all the time, simply by measuring things in nature. Okay, and then lots more. So when I say lots more, I mean like probably another 20 of these. So the idea is that all these are ways to think about quantum mechanics, but without changing the predictions of the theorist. So there's sort of a meta-narrative on top of the theory. All right, good. And in fact, so going sort of pushing into my religious theme, I love this quote from Chris Fuchs. And this is from one of his articles. And so we're going to be beginning to enter this realm which science touches, but nothing to say it has some boundary between religious and philosophy, and science and religion. And Chris makes this point in a forceful way. So go to any meeting on quantum foundations. It's like being in a holy city of great tumult. You will find all the religions with all their priests pitted in a holy war. The Bohmians, the consistent historians, the transactionalists, the spontaneous collapsians, the einselectionists, the contextual objectivists, the Everettiacs, and many more besides that. They all declare to see the light, the ultimate light. Each tells us that if we'll accept their solution as our savior, then we too will see the light. Okay. So it's kind of fun. But again, my point, is that the science, from a scientific point of view, it doesn't care what your interpretation is. It's just concerned with the objective predictions of the theory. All right, good. So let's sort of transition now. We've had our sorbet course. We're going to go into religion now. So I'm going to talk a little bit about my views of this. So we know about divine in sort of in two ways. So there is natural knowledge. Thank you, Mary. Natural knowledge of the divine, which is sort of general revelation. This is what we experience walking around as humanoids on planet Earth, as our ancient ancestors did, back in the caves. We have this weird thing called natural law, which is something that maybe has fallen out of fashion, but I think it's very much still important and relevant, which is that we have a sense of right and wrong just by being people, right? We see this in very early age children. That there is something like also the truth and falsehood is also something that we have a sense of, even though we don't know why. And we also have a universal quest for meaning. We want to know why we're here. We want to understand what our role in the world is, and so on and so forth. And we also have something called self-awareness. So we notice that the trees and the plants and the rocks don't have this thing. They don't have this thing called self-awareness. And also some limited awareness of what is beyond us. So we have the most intimate knowledge of our own internal nature, but we also have some limited knowledge by our senses of what's beyond. Okay, so the second way that we have religious knowledge is through what we call a revelation or revealed knowledge. And so there's particular revelation, so for example, through certain people or testimony, like the prophets, Moses, Jesus, the Bible, this sort of thing. But we also have personal experience as well. So we have things like prayer, worship, supernatural encounters. We also have art, we have music. These are also kind of personal ways of knowing the transcendent, in some sense, the divine. So these are the two sort of twin bases on which we have some theological discussion. And we can also combine the two. So there's this interesting argument that St. Paul gives. He says in Romans, for his invisible attributes, namely his eternal power and divine nature, have been clearly perceived ever since the creation of the world and the things that have been made, so they are without excuse. So here St. Paul is making the same argument that even though some people may not have the private revelation or the specific revelation, they have the general revelation the attributes of God clearly perceived in the world around him. So he's making a particular argument about a general phenomenon. Okay, good. So let's talk a little bit about theology. So I'm going to say a few things about this. So I want to give you sort of a classic example in my mind of what theology is. So there are many different ways of doing theology. As a Western Christian, I'm most familiar with the rational approach. And probably the best example I can think of is St. Thomas Aquinas. And if you've ever read St. Thomas Aquinas, I really recommend it. It's a fun experience. It's very different than anything you read as sort of a modern person. And the way he argues is quite illuminating. He basically gives a proposition, and he gives a series of objections to it. And the objections are not dumb objections. They're very smart and referenced objections. And then he gives his view, but I say, and he gives his view of the original proposition, and then after his statement, he gives his arguments for that, and then at the end he revisits the objections and shows how each of the objections are sequentially invalid or not correct. So it's a very systematic way of doing theology. It's really a nice example of so-called scholastic philosophical theology. And one nice example I like to point out is his 5 proofs of the existence of God. These are a little bit hard for us to understand. I think the terms, I was studying them last night, and the terms he uses are a little bit different than what we use today. But this idea of argument from motion of the prime mover, the argument from causation, from contingency, from degree, from final cause or end, these are all examples of rational philosophical arguments St. Thomas Aquinas is making about the nature of God. So I just put these up here as an example of the kind of rational discourse we have and how we want to use reason, philosophy, particular sources of knowledge to be able to reason and say something general about them. So I want to talk a little bit about some views people have to sort of reconcile or talk about the relationship between God and science. And one of the things I counter a lot in either online or in personal discussions is people have an interesting view. I want to describe it. It's what I call a law-like view of the universe. So they view that God exists, and he created the universe in some kind of mechanistic way. So there are laws, so that and the laws tell particles to do what they do. So if I release the ball will fall. The Earth goes around the planet. So these are the laws that God made. And God doesn't break his own laws, right? He sets them in motion, and so we can't intervene in that. So that's what we call it, the non-interventionist God. And so this view typically, if you follow it through to the end, basically you would also not really allow miracles because you don't want God to come and tinker with the machine. And really what it leaves as God is somehow external to creation. So this gives the clockwork universe, which is also sort of a deist conception of God. And I think this is a logically consistent view. You can hold this view, and I think argue it correctly. But I think, from my point of view, there are lots of problems with it. So I don't think it can account in any systematic way for again these testimonies of religion. For example, the miraculous that is not consistent with this point of view. And also, there's not really any good theory of agency in this description. So how does God intervene? How does he give agency? And even for the most intimate agent that we know ourselves, we don't really have a good theory of how we come along and do things of our own volition, our own will power, our own action. It's not really contained in this view. So I think, but I find this view a lot. People in the back of their mind when they're arguing about the relationship of God and the universe, I think ultimately have a version of this in their mind. So this is what I call the clockwork universe picture. So I think for me anyway, the more helpful view is, right. And so yes, so the title of this slide is God using the quantumness to sneak in. So this is about God and the quantum. And so some people have thought, because there's all this wave function collapse going, that's all random. So maybe the randomness that we experience is somehow God intervening in some unpredictable way to rule the world. Okay, so many respectable people make this. So for example, like John Chalmers, I think in his book about human consciousness, a very respectable philosopher, makes this kind of argument. Other very respected philosophers make this argument. I think this is a misguided view myself, simply because I think it takes a too small view of God. I think if we take the idea of God seriously as the creator and sustainer of the universe, if we take that seriously, then I think his role in the world must go beyond controlling how wave functions collapse. Right? And again, so I think a lot of this is about our trying to make sense of the way the world works, trying to put our theories or mechanisms of God on top of the world. And I think that's problematic in a lot of ways. Simply that I think our philosophies can get us in a lot of trouble about that. Okay. So I like to quote Albert Einstein. So God doesn't play dice with the world. In some sense, we know that the dice do get thrown in some sense, right? But okay. All right. So I want to put forward a different view. So this is my view, which rather than thinking about the universe like a clock, think about it like a lute. A lute is this musical instrument here. So here's a quote. For how could this universe have come into being or been put together unless God had called it into existence and held it together? Everyone who sees a beautifully made lute and considers the skill with which it has been fitted together and arranged, or who hears its melody, could think of none but the lute maker, the lute player, and recur to him in mind, though he might know him by sight. And thus is also manifested that which is perceived and moves and perceives all things, even though he be not comprehended by the mind. And the reason I like this analogy better than the watch analogy is because when you think about the watch gets sort of put up on the shelf, and eventually you have to come and tinker with it, or you wind it or something like that. But this analogy of the musical instrument is a more interactive dynamic. The universe exists in a way to be interacted with by creation in a purposeful and designed way. And I wish I could take credit for this. This was a great saying, but I was scooped by about 1,700 years. This is Gregory Nazianzus. So he was Archbishop of Constantinople in 360 something. So I like this analogy. The other point of view is I want to talk more about this idea of God and law, okay? Because I think we can get, again, messed up about when we're thinking about this. And so this is just an argument I'm going to make, and I just want to illustrate this, that the way we think about this, our philosophical construction of the concept can completely change the way we think about the relationship between God and creation. And so one example I want to give is the idea of properties of God. So usually in theology, I think I mentioned this in Aquinas, in traditional theology, we use negative language to talk about God because God is really outside of anything we can comprehend. But we can articulate precisely what God is not. And so this is maybe one of the ways we can get into trouble. But one of the traditional properties of God is omniscient, omnipotent, all these lists of things. So this idea of omnipotence is the one that's very all-powerful. So if we contrast this sort of idea of the Western idea, the one who can do anything, with this Eastern tradition, if you go look at this is an icon in the Russian Orthodox Church, the Christ the Pancreator. And the rough translation here is the one who does everything. So it's a subtle difference between these things, but it completely reorients our mind, our philosophical approach to these ideas. Okay. And so then I guess the second point I want to make here is that, this idea of what we call physical law. This is really something we put of ourselves, our own experience, because we know about laws. We create laws, we break laws, but we get upset when God breaks the laws we put on him, right? But if we reframe that idea of physical law as just regularity, and that's all science is quantifying regularity, then I think that liberates us from to a more cogent and perhaps I think consistent or accommodating view of the nature of divine. So we get thinking about God as not just someone that comes along and tinkers, but one who's literally responsible for everything all the time. I think it's a more complete theology of God's nature. All right. So, okay, good. So let's talk a little bit about now how religious thought and quantum mechanics can come together. And admittedly, they're very different domains, right? So most of what I do has absolutely nothing to do with religious thought. But there may be, but unlike Stephen Jay Gould, who would put these guys as non-overlapping at all, I think they do overlap a little bit. So, for example, like the beginnings of the universe, how things are sustained, analogies, and also a lot of nonsense. I'll talk about nonsense here in a little bit. So let's talk a little bit about how quantum world can inform our view of theology. So here's several points I want to make. The first is that it challenges a naive materialist worldview. So the role of observer or agency is fundamental in the theory, and so this idea of our role becoming an observer participant, I think it really goes beyond the naive materialist worldview. It is a fundamentally indeterministic theory we've talked about, and so we had a theory of Laplace that the universe was really like a closed clockwork thing. Everything was determined by the initial conditions of the universe. It really upends that philosophical system. This notion we're talking about, complementarity, coherence, entanglement, really have to expand our view of reality. We can't keep the same view of reality and be able to keep understanding how the quantum world works. And this is really a revolution in conceptual concept. So even practicing quantum physicists have not really internalized this. Okay? And so these ideas can also give us a new language, and I'll come to that here in a minute. All right, so I want to tell you 3 stories, short stories. And the first story is a story of nonsense. So often you hear, for example, I had an encounter with my Uber driver. I was driving into work one day, and she said, "What do you do for a living?" I said, "Oh, I work on physics." And she said, "Oh, do you do quantum mechanics?" I was like, "Yeah, I do." And she's like, "Oh, I've been reading about quantum mechanics. I'm so excited to ask you questions." And she said, "I've heard that if you concentrate real hard and act like you want to do something, like, oh, I don't know, just like something like make a lot of money, then the quantum wave function will start working in your favor and you'll start making a lot of money." Okay? And so I was like, "Oh, no, that's not the way it works." But the reason I tell the story is because it's sort of a story about our society. Because in the old times, when you had superstition, the superstition was attached so much to the most powerful mover of the society, which was religious science. We had religious superstition. Now, increasingly, the superstition is detaching from religion and attaching to now the most powerful force in our society, science and technology. So that was my first story. My second story is I was sitting at maybe 5, 6 years ago. I was sitting in a meeting of philosophers of science. I like to talk to philosophers of science. They're really messed up people usually. And this is the story illustrating that, because they were thinking about, they told their own story about how they were in an undergraduate quantum mechanics class. They were a physics major. They'd taken mechanics, electricity, magnetism, thermal physics. Everything was going well. They were doing well. And then they took quantum mechanics. And what they learned about the quantum world so disturbed this person, so shook them to their core, that they couldn't continue. They had to stop doing physics. They simply couldn't accept it. And so they switched and became a philosopher of science to try to have another way around it. So it shows, so the point of the story there is just to show that our view of the world really shapes us, and our ability to understand it and comprehend it and articulate how it works is really critical. And so these metaphysical questions, the ones that go beyond the science, are really the ones most people really care about. So that's why you see so much passion about these sort of religious questions, interpretation questions. Okay. And then the last story is a story about in my undergraduate quantum class. I had one of my classmates come up to me or discussing, and they said, "Oh, now we know about quantum mechanics. That means God can't exist." I said, "Oh, okay. Well, how do you get there?" I said, "Oh, well, because if God is all-knowing, He would immediately collapse all the wave functions, and then the whole universe would fall apart." Right? And so the story there is it's a little bit like an updated version of the old Jim. You know, can God create a rock so big He can't lift it? Right? So the problem there is not the science. The problem there is a lack of theological education, about knowing about even a little bit about the way God works and the way we understand Him. So yes, so that's my other experience is that I know a lot of people with lots and lots of knowledge about science and mathematics, but zero knowledge about theology, even the Bible. And so when you try to talk with people like that, it's really difficult. It's like you try to come and talk to someone about history who's never taken a single history course and doesn't know nothing about history. You can't have an intelligent conversation. So there's, even though they're very intelligent, you have the impasse. Okay, good. I want to sort of end here, or come close to ending, by talking about this. So I want to talk about what someone besides me thinks about God and quantum mechanics. Unfortunately, Jesus has very little to say about the subject, and indeed the Catechism says nothing, and most theologians say nothing as well. But we have our hero, Cardinal Ratzinger, having a beer with you to the answer, and he has some things to say that I think are very helpful. And I just want to go, I won't go over them in detail, but I'll refer you to them. He makes several points here in his thing. I'm only going to tell you, I'll read one of them to you, but there are other ones for you. So one is how seemingly contradictory realities from different points of view can point to a whole, that we can't comprehend the whole in its entirety, but only from different points of view. And we'll talk about that in a moment. This idea of how quantum waves can be a simile for God's action and existence as being formed of relations, which I think is interesting. He basically credits this to Augustine. How we must embrace our role as active observers to experience life. So this idea that we can't be entirely passive to experience life, we have to become participants in some sense in the universe. Only those who ask receive an answer, and the neutral curiosity of the mind can never enable one to see. You have to become actively engaged to be able to enter into the reality. So I'll read just a short excerpt from the first one. Father, could you hold my microphone here just for a moment? Thank you so much. I'll be quick. All right, so the Jansius St. Cyrion once made the thought-provoking remark that faith consists of a series of contradictions held together by grace. He thereby expressed in the realm of theology discovered that today in physics, as the law of complementarity, belongs to the realm of rational scientific thought. The physicist is becoming increasingly aware today that we cannot embrace given realities, the structure of light, for example, or the matter in general, in one form of experiment, and so in one form of statement. That on the contrary, from different sides, we glimpse different aspects which cannot be traced back to one another. We have to take the two together, to the structure of the particle and the wave, without being able to find a comprehensive explanation as a provisional assessment of the whole, which is not accessible to us as a unified whole, because of the restrictions implicit in our point of view. What is true here in the physical realm as a result of the limitations of our ability to observe the truth is an incomparably greater degree true in the spiritualities and God. Here too we can always look for one side and so grasp only one particular aspect, which seems to contradict the other, yet only when combined with it is it a pointer to the whole, which we are capable of stating or grasping. Only by circling around and looking and describing from differently, apparently contradictory angles, can we succeed in alluding to the truth, which is never visible to us in its totality. And what's interesting here, I think, is he also quotes Niels Bohr. So Niels Bohr is one of the founders of the quantum theory, and he points out he introduced the notion of complementarity in physics, but in his original physics article, this is Bohr, Atomic Theory and Natural Works, published in German in Berlin in 1931, he introduces us to this notion of complementarity. He references the complementarity of God's justice and mercy as one example of this, as apparently contradictory, but nevertheless complementary aspects of the two things together. So this is Ratzinger's Introduction to Christianity. So he goes on for about 4 pages about this stuff. So it's very interesting, so I recommend it if you're looking for something fun to read. All right. Before I go further, how are we doing on time? Should I be done now? I can keep on. I've got a few more slides. Good. All right. Good. So I want to talk about this last topic, this idea that I like to call information as the most spiritual physical thing. All right. So what is information? So it's playing an increasingly important role in physics, so I work with it all the time. It's important for things like quantum computers, which can execute algorithms faster and more efficiently than any classical computer. Quantum cryptography, being able to hide secrets. Quantum control, and so on and so forth. But what is it? What is this information we speak of? Whose information? My information? Your information? So information is physical. And this was one of the great statements of Rolf Landauer, who liked to say that information is physical. But it transcends the physical in the sense that we encode it in certain physical things, like for example, in your computer, you find it's made up of transistors. The transistor either has a voltage or not a voltage, and that encodes a logical 0 or logical 1. So there it is sitting in your computer. It's got information, but I can also do things like transfer from one thing to the other. So if I send you an email, the information is no longer in your, or it may still be in your computer, but now it's been transferred to you. So it's physical, but it's yet abstractable from it. And furthermore, the value lies in the eye of the beholder. What may be very important information to me, what may be absolutely meaningless to you, and vice versa. But in some sense, it transcends any one observer in its information content. And so this is that's why I think it's something like the spiritual, because the spiritual world is somehow connected to the physical world in a way we don't really understand. And that's one of the interesting things about our condition. We don't really understand that in a deep way, but yet it goes beyond that, right? Because we think it exists independently also from the physical as well. And so I think that can give us at least a simile to begin to understand some of the spiritual realities. Okay, good. So one example of this information that I want to give, because Father Bartas liked this, and so I'll give you this as an example, is the late Stephen Hawking, who recently died. He got, one of the things he was famous for is he said, what happens if I take information and I throw it into a black hole? All right, so a black hole is this astrophysical thing out there. It's so dense, light cannot escape from it. Is that information destroyed forever? There is the Encyclopedia Britannica, it goes into the black hole, it's gone forever, it's just some mass now, right? Well, that was what he claimed, but other people thought not so fast. What about, because that contradicts quantum mechanics, because quantum mechanics has a principle called unitarity, which says that I preserve something, some property of the quantum states when I make physical transformations on it, okay? And we can quantify that aspect of the quantum states as information. Good. And so a man named John Prescott, he's just up the road from you guys, up in Caltech, he argued the opposite, because quantum mechanics violates that principle. That would violate quantum mechanical principles, so we have to then somehow change this view of black holes in some way. And this is sometimes called the black hole information paradox or the information problem. What it did is it set the two great twin discoveries of quantum mechanics in the 20th century at war with one another. The theory of quantum mechanics at war with the theory of general relativity. So this is, again, one of the examples I could give. The science doesn't just fight with other people, science fights within itself. So this is a great example of this. So it's an inter-science fight. And what happened, essentially, is eventually Stephen Hawking conceded that he lost. That in fact, information is in fact not destroyed by the black hole, but has a way of being preserved by it. And so they had a bet, and John Prescott won this bet because Hawking conceded. Good. So, how actually is this happen? How does the information somehow be preserved in the black hole? What happens? So no one knows. You can't really do experiments on black holes very easily. But one idea that the same guy, Prescott, had with a colleague of his, Haydn, was the following. What if, as a particle was coming into this black hole, something interesting happened? We know in the vicinity of the black hole, so one of the things that Hawking predicted is that in the vicinity of the black hole there would be these things called particle-antiparticle pairs sort of popping into and out of existence all the time around the event horizon. That's the point of no return of this black hole. And these guys argue, what if somehow you could take information encoded in this particle as it goes into the black hole, you could use this particle-antiparticle pair as a kind of vehicle. So it combines, say it combines with one of these particles, but then it transfers the information onto its twin over here. And the information is able to escape away. Okay? So that was their way, just in a very rough way of speaking, how they were able to show how, or at least propose a mechanism for preserving information around a black hole. It's simply because it never enters it in the first place. It acts like a mirror of the information. It accepts the particle, but it rejects the information by using the antiparticle of the Hawking pair to be able to carry the information. So we had kind of a crazy idea. This was with a student of mine recently. And we said, well, we could study this exact same mechanism, but in a more down-to-earth place. What if you did the same thing with the superconductor? So what if you had, for example, a normal metal with an interface with a superconductor? What would happen there? You can ask the same kind of question. I take electron, I encode some information, electron, I throw it in the superconductor. What happens? And it turns out the same idea these guys had can be exactly mapped onto the physics of this normal superconductor interface. So a superconductor is just a metal that has no resistance. And one of the basic ingredients of a superconductor is that they're made up of these things called Cooper pairs, which is the elementary excitation. And so as electron goes in, what happens is that it can only go in with a partner. It drags electron in from the interface, forming this Cooper pair, but then it shoots out something called a hole, or absence of electron. And what you can see is very interesting is that the information I encode, for example, the spin electron, it's exactly mapped onto the hole exiting back into the metal. So this information transfer happens exactly using these quantum information tricks. So we got a lot of publicity for this recently. So that was fun. Okay, good. So here I don't have conclusions, but I have an outlook. And here is my outlook. So the world is a mysterious place. We find ourselves in this strange, mysterious world. We try to make sense of it. I think bad mental constructs can make it more confusing, but if you can make a good mental construct or a good philosophy, it can have three properties. First of all, enlightening, to make sense of the world. Secondly, fruitful, allowing you to be able to go forward in a productive way. And then predictive, things that will now allow me to go and do things in the future that leverage my proper understanding of the world. And I want to, my statement is that this is not only true in science, this is true in religion. You've heard the expression bad religion, right? And you've probably seen bad religion firsthand, right? So there's also a thing like bad science, and so I think this is true in both places, all right? Again, the common feature of both, even though I think they're very different disciplines, they have overlapping regions, it's a complicated thing, the commonality is we're all after the truth. We're trying to understand the truth, and that's our ultimate gain, our ultimate goal. I guess what I also want to leave you about I don't want to reduce either science or religion to simple things. They're not simple things. These are very complicated things. And they have weird things that go beyond our simple and naive understanding of them. And that's I think that's good, that the world is a bigger place than we can understand or experience. If you think about quantum mechanics has only been known for about 100 years. The vast majority of our ancestors had no idea any of this stuff. And yet, so this shows that there's a whole worlds out there we simply don't know, we don't understand. And what I want to also say is that we can expect some harmony between them. So we can expect places where religion and science come together, both within themselves, but with each other. But we can also expect dissonance because we have an incomplete understanding as well. I think both together can help lead us to the pursuit of the truth. Okay, so I think I'll end there, and I'll be happy to take questions and discussions. Thank you. Barbara, do you want to moderate? You want to moderate the questions, or
so you go ahead and choose.
Okay.
Yeah, since none of the theories you listed can ultimately.
Why don't you take my microphone?
Since none of the theories you listed can ultimately be demonstrated, why do they persist, especially string theory?
Okay, so there are 2 points there. So there's the theory of quantum mechanics, which not only can be demonstrated, but has been. There are the interpretations of quantum mechanics. Those have the same empirical interpretation. So one of the reasons people argue about them is because they believe one of them is true and the rest of them are false. And so it's a metaphysical question, and so they argue about it not from a scientific point of view, but trying to understand the correct metaphysics. Your second point was you asked about string theory. So let me just say a word or two about string theory. So remember those numbers I showed you towards the beginning of the talk about the anomalous magnetic dipole? So the theory that predicted that number is based on something called quantum field theory. So this is a generalization of quantum mechanics to include relativistic physics. So relativity is what happens when I have velocities going very close to the speed of light. So we have a theory that incorporates both of those. And that's our most successful theory of nature. That's called the standard model of particle physics. And now all particles that have been predicted have been discovered. All the parameters have been nailed down. That is our operational theory of the fundamental physics. Now, some people believe that that's not the whole story, and that there is a more fundamental theory of nature. And of course, we can keep going to higher and higher energy or smaller and smaller length scales. And one candidate, so first of all, we don't know that this theory exists. But if it did exist, one candidate theory is the thing you mentioned, string theory. And that's the idea that you don't have particles as the most elementary things, but extended objects like strings or loops or even membranes. And so I have lots of friends that work on string theory, so I don't want to say bad things about them. But it is a candidate theory of nature. It hasn't been proven or disproven. It's just out there. They are searching for ways in which you could try to disprove or prove it, but it is science in the sense that it does make some predictions. But often the predictions it does make are kind of discouraging. So one of the most discouraging recent predictions is that we live in one of 10 to the 23 or so possible universes, and so therefore we can't predict the properties of our universe because it's just one of 10 to the 23, and so it loses a lot of its predictive ability. So that's kind of a discouraging result. But in principle, it could make some kind of testable prediction. So I think it is in principle science, but more often than not, I see my friends describing it as a very fruitful branch of mathematics. If you read string theory papers, they're very, very mathematical. So I do a lot of mathematics, but they do even more abstract mathematics than I do. And so that's sort of the story there. Okay, yes?
In layman's terms, why exactly do you dislike the many worlds theory, especially? I mean, because coming from a non-scientific background, it seems like a useful framework to reconcile both. For example, from a theological point of view, God's omniscience and free will, like in the sense, like at least it seems to me.
Okay, so I guess one answer is that we only see a single universe that we live in, and this theory has huge metaphysical baggage. It basically says that every time, say, an electron goes through one of those two slits, that splits off a whole new universe that we can't see. That seems to me like making a whole new metaphysics to try to explain a very simple thing. Right? If I made a whole new metaphysics to be able to try to explain, why a ball rolled or something like that, you would laugh at me. But because we can't wrap our minds around the quantum. If we could expand our minds, I think, and say we accept the fact that particles can go through both slits at once, then that wouldn't be an issue, right? Because they philosophically reject that. I think I just view it as a kind of even absurd metaphysical claim. Now, what it has to say about theology, you mentioned something about the omniscience and free will. I don't think it does either of those theologically, because all the many worlds theory says is everything that can happen does happen, right? And if everything that can happen does happen, there is no free will, because everything happens. Every bad thing, every good thing, etc.
So I kind of have a two-part question. So what you did is after having gone through all the metaphysical interpretations of quantum mechanics, we kind of use those as a lens through which to view theology, but I guess the same thing kind of works too. If we had started from the beginning and said, oh, the many worlds interpretation is true, then we'd probably come off with a very different theological view at the end of it. So it kind of works two ways. We have an idea about how God works, which gives us an idea about which quantum mechanics interpretation to understand, which then tells us about God. A couple questions about this then. First off, do you think since all of these metaphysical theories are based on categories that to some extent come from our everyday experience, do you think that any one of these ways of looking at things actually does capture the deeper reality behind it? And for that matter, do you think that any of these other interpretations, might give us other insight about the way God works?
Yeah, it's a great question. So one of the things I gave at the other talk I presented this to is I said, what does the Bible have to say about quantum mechanics? And I found one sort of semi-relevant verse. I actually went to the internet because the internet knows everything. And so I said, Internet, what does the Bible tell us about quantum mechanics? And it gave me like a dozen verses, and I was amazed. Unfortunately, none of them told us anything about quantum mechanics. But the one that was sort of semi-relevant was, I may have it here. It's kind of fun. Okay, this is from Jeremiah. I'm applying this to interpretations of quantum mechanics. Every man is stupid and without knowledge. Every goldsmith is put to shame by his idols, for his images are false, and there is no breath in them. They are worthless, a work of delusion. At the time of their punishment, they shall perish. So all that is to say, these interpretations are, in some sense, our idols. Right? It's our things that we create in our mind to try to make sense of the external reality. My suspicion is that none of them are right. My suspicion is that at some point we'll have a deeper understanding, and then people will say, why didn't we think of that earlier?
What do you think quantum mechanics has to imply about free will? In particular, are our minds physical and yet at the same time transcend the physical? Because there's a great deal of uncertainty involved when it comes to quantum mechanics, while at the same time, there's an intentionality when it comes to our decision making. So there's a great deal of debate among philosophers in the realm of philosophy of mind on this topic.
Yeah, thanks. It's a great question. So that was one of the things we were debating at this other meeting I was at, and it's a very common question to come up. Again, because of the indeterminacy of quantum mechanics, the fact that everything is not somehow preordained, it leads. So I remember earlier in the talk I referenced this Laplacian view that everything is determined by the initial conditions of the universe, and therefore we have no free will because our actions are constrained simply by our past initial conditions. Everything that will be must be. And so this is actually there's a thread in theological thought, right, that follows this. So, for example, like Calvin's view of predestination goes into this point of view. And as for what it has to say about free will, the short answer is I don't know, but I will say that indeed the fact that the quantum mechanics is indeterminate, I think gives us a clue that we shouldn't think about the rest of our actions are forced or determined. So I think that would be my first answer. But I would also caution putting too much into that, so that this view I put earlier about the indeterminacy is somehow God's wedge into the physical universe using these indeterminacies to work His will in the world. That could be a view, and some people defend that view. But I think in my opinion, it's sort of too small a perspective on God's action.
Thank you so much. This was a really wonderful talk. I really enjoyed it. My question is about St. Thomas and the quantum. So, you mentioned St. Thomas's arguments for the existence of God, and those are arguments of classical metaphysics. So, they rely on, at a minimum, some sort of principle of causality, some basic logic, some Aristotelian metaphysics. And there are some people, at least there's some tradition in philosophy of science today that says quantum mechanics shows us that we can't trust classical metaphysics, or the more extreme ones say we can't even trust classical logic. So how do you respond to that sort of skepticism about classical metaphysics that's generated by the strangeness of quantum phenomena and their interpretations?
Wow, you guys know a lot of stuff. I'm impressed. Okay. Yeah, so very good. Indeed, so in Ratzinger's book, he also addresses this question about, so in some sense, it's true that quantum mechanics really presses on Aristotelian logic, right? And he acknowledges that. But however, that is not to say that quantum mechanics is somehow irrational or illogical. It has, in some sense, for example, it's a mathematical theory, right? So mathematics is based fundamentally on logic, and so that's, I guess, one point to make. The point about the quantum superposition. So in Aristotelian logic, you would say, you know, if I have a particle that goes through the slit, it's got to go through the left slit, or it's got to go the right slit. There are no other options, right? Whereas in quantum mechanics says, at least on the face of it, that no, I have to take into account the fact that they go through both slits at the same time. So in some sense, they exist in this expanded reality, right? And so in the quantum world, people have tried to sort of go down that realm. There is something called quantum logic. People have tried to expand the rules of logic. If you take just sort of like Boolean logic, or it's based on, and you try to expand it, you try to deny certain axioms and expand certain axioms. People have done that. I don't view that as a particularly helpful point of view. But yeah. So I think I can certainly see the argument, and I'm sympathetic with it. Yeah, but I'm not sure what more to say other than read Ratzinger, because he has some stuff to say. Good. Okay. Any other questions? All right, then we're all finished. Thank you.